Okay, so a big aspect of pretty much graphs in general is a special class of graphs called trees. Now, trees are important for many different ways and many different reasons, but the whole idea being is we've looked at this fact that if we have a UV walk and we can get a UV path, then we also had this situation if we have a walk from every vertice to every other vertice, in other words, you can make your way from any vertice in the graph to any other vertice in the graph by means of a walk. It is a connected graph. And that just basically means you don't have any isolated vertices or there is no disjoint situation happening. And a connected graph, as you may be starting to realize, is actually a very important concept. So now a tree is going to be connected to this idea with the path situation, and it's going to lead to a lot of useful algorithms and stuff. So we're going to start off by first bringing in some more definitions, and these definitions are basically to cement your definition of a tree. So the first one is going to be the concept of basically you have a graph of a cycle. What can you call something that doesn't have a graph that doesn't have a cycle? So in regards to this, we're going to bring in a new word or new terminology basically that basically means acyclic. And that means that it's just going to be a graph and it's going to be a simple graph which has no cycles. So now majority of the times when I refer to graph in this context, it is going to be in terms of simple graphs. However, if a graph doesn't have any cycles, you should be able to wonder if it's going to have any self loops or any multiple edges available. Just by thinking about what is a cycle and what is a multiple edge and what is a self loop. So that's just something to think about. So now we're going to go through the definitions, the introduction to the definitions. So the first one is just, hey, here's a name for a graph that has no cycles, acyclic. So acyclic, a graph with no cycles, specifically a simple graph. Okay, so next up we have this concept, and we literally are going to do this. We're going to introduce the concept of a forest before the concept of a tree. So a forest is essentially just an undirected acyclic graph. So if there are no cycles in your graph and no other context required, you have a forest. So a forest is an undirected acyclic graph. And again, simple graph. And now we're going to narrow down the concept of a forest. So essentially, and if you can visualize this in terms of actual forests and trees and stuff, what we have right now is we're basically saying, listen here, there just must be cycles in the graph, and then it's a forest. And now we're going to discuss the concept of, well, when you think of something like a tree has to be, all the branches have to be connected to each other. So in your forest, a branch of another tree does not necessarily have to be connected to the tree next to it. This is not Pandora. We are working with like some of the special trees around here. Okay. And the sirens are gone, so let's continue. So again, we have this now situation of we want to describe or define what a tree is and the difference between a tree and a forest. So a tree is actually a connected, undirected acyclic graph. So all the branches all the bits of the graph have to be connected. So we have a tree. So it's connected acyclic graph. And again, it's a simple graph that we're talking about when we look at this. So let's actually draw this, because the drawing of it's going to make a little more sense. So we have firstly a graph with no cycles. So a graph with no cycles could literally just be something like this, technically. Let's call this G1. It could also just be something like this, G2. Or it could be, and yes, I'm just going to keep an order 6 graph as an example here, G3 situation. So that technically they're all acyclic graphs. Another concept of an all acyclic graph is 1, 2, 3, 1, 2, 3. Let's do, that is also an acyclic graph. Right. So now we narrowed this down. We say, okay, those are all acyclic graphs. They don't have any cycles in them. Please double check. And then we have a forest is an undirected acyclic graph. So, what I could have done, and we haven't done directed graphs yet, but let's just do it anyway, just so you can see the narrowing down situation of this. You could have an acyclic graph, which basically the idea is when you have an edge and it has an arrow through it, it is only going in that direction. So when you start looking at things like a graph with no cycles and it's directed, you could have this situation where it's very similar to this G4 area where we just have one piece missing, but we could technically have something like that. So it looks, at first look, if you don't look at the arrows, it looks like it has a cycle in it, but when you look closer, it doesn't actually have a cycle in it because of the direction of the situation. Or let's just leave it like that. It has a very specific direction, and G5. So we now have the concept of a forest, and a forest is an undirected acyclic graph. So a forest is all of these. That's a forest, that's a forest, that's a forest, and that's a forest. Okay, so those are all forests. And now we're going to narrow it down even further. And we say, okay, well, trees, and you have trees in your forest in real life, so this should help you with the visualization. A tree is an undirected connected acyclic graph. So it's undirected, so it fits into the forest, but it's a connected acyclic graph. So when you look at these graphs as is, they are not all, well, one of them is connected. This one is connected in that you can get from any vertice to any other vertice by a walk. So this is also a tree. So it is a forest, but it is also a tree. However, and now we're going to look a little bit deeper into this. If we go into the forest graphs, there exists tree graphs inside the forest graphs. See where I see that, it kind of makes sense with nature. A lot of graph theory people walked around nature all the time kind of situation. So when you look at this, and let's start with G1, you could almost see it as you are looking on top of a forest and you see the tops of the trees. So this is a tree, 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 this is a tree. Because the definition of a tree is it's an undirected, connected acyclic graph. Right. And what does a connected graph mean? It has a UV walk from every vertice to every other vertice. So if you had a graph which just sits with like one kind of situation, you will have, your one node effect. Okay, next up you have G2. And now again, you can break this into two trees. So that is technically a tree, and that is technically a tree, because that is a connected, and I'm talking about that, by the way, I'm looking at that one, that is a connected acyclic graph. And then when you look at G3, you have three trees. You have, there's a tree, there's a tree, there's a tree. So it's a tree of two nodes, a tree of two nodes, a tree of two nodes. And yeah, I'm going to start bringing in some ways you can describe this. This will be a tree of three nodes of order 3, basically. This would be a tree of order 6. 1, 2, 3, 4, 5, 6 nodes, basically. These are all T1s. So this is a forest containing 6 T1 graphs, subgraphs. So basically subgraphs. So that forest contains subgraphs, and those subgraphs are trees. And this is slowly leading you to some other things. But now there's one other aspect. So if you have, and we're just going to bring this up here, think about trees and branches and so on. And we're going to use the term branches frequently as well. You can then go from a branch to a leaf. So one of the things to note is that a leaf is a 1-degree vertex, which is also known as a pendant vertex. So you have multiple names again for a concept. So let's just add it in here. We have a leaf, and it is a 1-degree vertex in a tree. It's a leaf. So in regards to that, when you had to, for example, look at T3, so let's look at one of these. This one here and this one here are leaves. Okay, so let's just color code this quick. That is a tree, and you'll have your combo. Now, because this is mathematics, there's obviously other ways that you can define them, still getting the exact same outcome. So another way that you can define a tree is you can go about it in a slightly different way, and you can say, okay, it's an undirected, connected graph without any cycles. And you're like, well, yeah, we literally just said that. This is just written in a different way. And again, it's a case of this is a simple graph. And then you can say, and this is where it comes in that, again, you can define things differently, but they mean the same thing. A forest is a simple graph in which every connected component of it is a tree. And this automatically combines the fact that it must not have any cycles, because if all its components, and when we talk about components of a graph, we have something like this, every connected component, let's just do this as an example. We can break up that graph that I just drew into 2 components, so 2 sections essentially. Or you could have, let's make it slightly more complicated. That one could be broken up into 3 components, and where that is a component, that is component, and that is a component. And it doesn't just have to be, for example, something that doesn't have any cycles. And this is why I refer to the fact that the moment you say the connected components are trees, you have it that it's a forest, because you could have had a graph like this, and you would have essentially 2 components, you know, that section there and that section there, but they both consist of graphs which are cycles or have cycles in them. So the idea behind this is the moment you say it's a simple graph where every connected component, and we've shown now how you can write connected components, is a tree. So that one, neither of those are trees. So you see how it narrows it down and automatically engages with the idea that it has no cycles in it by utilizing the definition of a tree, and that's where we get back to it. Okay, and before we move on, I also just want to talk about something referred to as isomorphic. And the idea behind that is basically if it's isomorphic, and you do this in math modeling, it is going to have the same shape, essentially, or the same structure. So when you have, for example, that, and I'm trying to do this so that it comes out like I mean it, that, or that. When you have to look at that, those are all isomorphic to each other. They're all representing the same thing, essentially. So you have one node of degree 3. There's that node again. There's that node again. And the other nodes there of degree 1, the leaves. So the idea behind that is you can essentially redraw this graph here to look like those. And you're not adding in anything extra. You just kind of like position it in slightly different. So the idea is to think about whether or not it is isomorphic or not. And isomorphic, it has the same structures. It's just the way that you've drawn it looks slightly different and so on. So that's just something to remember and take note of because it's going to become very useful in the challenge question and also useful in regards to just thinking about the types of trees and stuff that you can have. Okay, so the last thing we're going to cover in this introduction to trees is just two really important theorems related to it. We are going to cover a bunch more theorems as we move on. But the first one is a graph is a tree if and only if there is exactly one path between every pair of its vertices. And one of the things just to note here, this if and only if, you'll see it in your text sometimes as, an if with an additional f to it, if and only if. It is a special type of theorem. When we get to theorems pretty soon, when we go into more depth with it, I'll discuss the importance of, the statement. But the whole idea here is if a graph is a tree, there is exactly one path between every pair of its vertices. Why is there exactly one? Because a tree is an acyclic graph. And if you don't have a cycle, there is only one, path between every other vertice kind of a situation, because something with a cycle, and again, I'm just going to use the very standard, order 4 graph here. If it has a cycle, then you can get from this red one to this one, either in that direction or in that direction kind of a thing. But if there was no cycle, so you had that situation where you have your 4 vertices and there's no cycle, you have something like that. In order to get from here to there, you can't go in this direction because there is no edge there. You have to go in that direction. That's what this theorem is saying. It's saying, listen, if it's a tree, there is only one path between every pair of vertices. And remember, your connected graph is a situation where there is a path between every pair of vertices. There exists a path between every pair of vertices. So what we're saying here is a tree is a connected graph again, and it has no cycles, but this theorem is just stating in a slightly different way. And then there is the second theorem here. And the second theorem says, okay, you have a tree, it consists of a vertice set and an edge set, and it's an order n. And if it's an order n, then its size is n minus 1. And again, this comes back to the idea that it is a connected graph. So if it's a connected graph, and we are going to eventually cover the fact that it's minimally connected, you're going to have this situation of if there are no cycles, the number of edges is going to be the number of vertices minus 1. So let's just have a look at, some examples of trees here. So let's have that as an example and that as an example. So if you just go ahead and look at that, you'll see, okay, this is an order 4. And if you go count the edges, 1, 2, 3, you have 3 edges for the size. And again, here it's order 4, and you have 1, 2, 3 edges for the size. Order 4. So these theorems will eventually add up, and the theorems can also define what a tree is in this case. So there's going to be the equivalent definitions for the tree, or if you look for different properties, you'll be able to use the alternative properties to identify if it is a tree.